Good morning, everybody. Today we will start a new topic on computational methods for conduction heat transfer. Now, if we look at any general second order equation given by A del 2 phi del x2 plus B del 2 phi del x del y plus C del 2 phi del y2 plus D del x del phi del x plus E del phi del y plus F into phi equal to gxy. If the coefficient A, B, C, D, E and F are either constants or functions of only x and y, do not contain phi or its derivatives, it is said to be a linear equation. That means A, B, C, D, E, F, these coefficients are either constants or functions of only x and y. They do not contain phi or its derivatives, then it is a linear equation. Otherwise, it is a nonlinear equation. An important subclass of nonlinear equations is quasi-linear equations. In this case, the coefficients may contain phi or its first derivative, but not the second derivative. If g equal to 0, the equation is homogeneous. Otherwise, it is non-homogeneous. Now, the mathematical character of the equation can also be determined from here. We can find out b square minus 4ac. If that is less than 0, then the equation is elliptic. B square minus 4ac, if it is equal to 0, then it is parabolic equation. And b square minus 4ac, if that is greater than 0, then the equation is hyperbolic. So these are different conic sections, and these are associated with these coefficients, and we can sort of remember that in our subsequent part of the lectures. Now, the unsteady Navier-Stokes equations are elliptic in space and parabolic in time. At steady state, the Navier-Stokes equations are elliptic. Why I have mentioned Navier-Stokes equations, x direction equation, y direction equation, z direction equation, or if it is cylindrical polar or spherical polar, the equations are basically momentum balance in different coordinate directions, and that is why these are set of equations. The Laplace equation and Poisson equation are generally associated with the steady state conduction heat transfer. These are also elliptic equations. The wave equation is hyperbolic equation, and the equation for unsteady state conduction heat transfer is a parabolic equation. Now, Poisson's equation, del 2 phi del x2 plus del 2 phi del y2 plus s, and if we substitute phi by temperature or define temperature as phi, and S is the source term, volumetric heat generation rate, then it becomes Poisson's equation. Del 2 phi del x2 del 2 phi del y2 equal to 0. If phi is temperature, then this is steady state heat conduction equation. Wave equation I have already mentioned about on this equation, that this is hyperbolic equation. And heat conduction equation, unsteady state heat conduction equation, which is del phi del t equal to b del 2 phi del x2. If phi is temperature and b is thermal diffusivity, then this is unsteady state heat conduction equation. For unsteady two-dimensional problems, the appropriate flow equation is del phi del t u del phi del x v del phi del y equal to d del 2 phi del x2 plus del 2 phi del y2 plus s, where phi is the transported quantity or transported property. It can be any of the velocities, and d is the diffusivity, molecular diffusivity. In case of flow equations, it will be viscosity, and S is the source term. So the formulation of a problem requires complete specification of the boundary and initial conditions in addition to the governing equation given above. Now, boundary conditions may be Dirichlet condition, maybe Neumann condition, or maybe mixed condition. If it is Dirichlet condition, then the value of the dependent variable will be directly specified. For example, here over A1, we have said that value of the dependent variable is directly known. Neumann condition is the derivative of the dependent variable that will be known. Like A2, this zone, we have shown that it is Neumann condition. The derivative of the dependent variable, in this case temperature, is known. And next is the mixed condition, which is basically given in this form. So these are the possible boundary conditions we will come across. Now we will just very simple way define a domain and the grid spacing, and we have drawn a network of horizontal and vertical lines and provide coordinates for locating the points in the domain. Like if this is ij, this is I plus 1j, this is I minus 1j, this is ij plus 1, this is ij minus 1, this is I plus 1, j plus 1, this is I minus 1, j plus 1, this is I minus 1, j minus 1, this is I plus 1, j minus 1. So del x, del y are the grid spacing. This can be uniform, can be non-uniform. Now, finite difference representations of the derivatives are obtained from Taylor series expansions. For example, u at I plus 1j is uij plus del u del x at ij into delta x, del 2u del x2 at ij into del x square by 2, and higher order derivatives subsequently will appear. We have for the time being neglected. Now from here, if we want to find out del u del x at ij, we can write ui plus 1 j minus uij by del x. We can also, since we have moved, for example, this term to left hand side and all other terms we have moved to right hand side, and then if we rearrange all these truncated higher order derivatives and higher order terms divided by delta x, because we have taken del u del x at ij, so remaining all the terms we have divided by delta x. And from here we can say del u del x at ij can be expressed as u at I plus 1j minus uij by delta x. And since the entire truncated series, in that entire truncated series, the highest order term will be of the order of delta x. So this is called first order forward difference. I plus 1, this point is located ahead of ij. I plus 1j is located ahead of ij, and that is why we are calling this forward difference. Similarly, we can also write Taylor series expansion involving I minus 1j point. Then ui minus 1j is uij, again plus del u del x at ij multiplied by minus delta x plus del 2u del x2 at ij multiplied by minus delta x square by 2 del 3u del x3 at ij minus del x cube by 6. So alternate terms will be positive and negative, we can see. And here from here del u del x we can write as uij minus ui minus 1j by delta x. And again the truncated series, the highest order term is of the order of delta x. So we can call this as first order backward difference or rearward difference scheme. Now from these two we can easily write del u del x at ij, that can be given by, from equation 1 and 2, ui plus 1j minus ui minus 1j divided by twice delta x. And then the highest term of the truncated series will be of the order of delta x square. So this is second order central difference of first order derivative. Now if we, in a similar way, if we basically from equation 1 and 2, if we add them, we will get this ui plus 1j ui minus 1j equal to twice uij plus del 2u del x2 at ij delta x square plus del 4u del x4 at ij delta x power 4 by 12 and other higher order terms. From here del 2u del x2 we can write as ui plus 1j minus twice uij plus ui minus 1j by delta x square, and remaining higher order terms, where the highest term of the truncated series is of the order of delta x square. Now here this is the expression for central difference second order derivative. Second order derivative, its central difference expression, and accuracy is of the order of delta x square. Now, combination of such finite difference quotients for partial derivatives form finite difference expressions. For the partial derivative, we can find out the finite difference quotients for each derivative. Like del 2 grad square u equal to 0. This is a Laplace equation. Now that means del 2u del x2 plus del 2u del y2 equal to 0. So finite difference quotients can be written as u I plus 1j minus twice u ij plus ui minus 1j by delta x square, ui j plus 1 minus twice uij plus ui j minus 1 by delta y square. So this plus is not very clear. This will be ui j plus 1. Please be careful. This is j plus 1. So from here we can write ui plus 1j plus ui minus 1j plus lambda square uij plus 1 plus uij minus 1 minus twice 1 plus lambda square uij equal to 0, where lambda is the mesh aspect ratio, that means delta x by delta y. Now, if we solve the Laplace equation on a domain that earlier we have seen figure 1, basically some such domain. So we can write uij is ui plus 1j plus ui minus 1j plus lambda square ui j plus 1 plus uij minus 1 divided by twice 1 plus lambda square. And if lambda x equal to lambda y, then it is simply ui plus 1j plus ui minus 1j plus ui j plus 1 plus ui j minus 1 by 4. So it can be said that many other forms of difference approximations can be obtained for the derivatives which constitute the governing equations for fluid flow and heat transfer. The basic procedure, however, remains the same. The same approach can be made or can be followed for the mixed derivatives also, like del 2u del x del y. Del 2u del x del y, we can write del x of uy. Then del 2u del x del y, we can write del x of del u del y. Del u del y at the point I plus 1 minus at the point I minus 1. So I plus 1 minus I minus 1 j, del u del y at I plus 1 j minus del u del y at I minus 1 j divided by twice delta x. This is central differencing. Then individually del u del x at I plus 1 j and del u del y at I plus 1 j and del u del y at I minus 1 j, we express following central difference. And then the final expression, finite difference quotient for del 2u del x del y becomes 1 by 4 delta x into delta y multiplied by, within bracket, u I plus 1 j plus 1 ui minus 1 j minus 1 minus ui plus 1 j minus 1 minus ui minus 1 j plus 1. And this is basically second order accurate in both the spatial directions. So we can see that first order forward difference, this is the truncated series, and in the truncated series the highest term is delta x. First order backward difference, this is the truncated series, and here the highest term is delta x. Second order central difference, this is the truncated series, and highest term is of the order of delta x square. So that is why it is second order accurate, and these are first order accurate. Now also we have to see that finite difference representation of a partial difference differential equation is consistent if the limit mesh tends to 0, that partial differential equation minus a finite difference equation or finite difference equivalent equal to limit mesh tends to 0 within bracket truncation error equal to 0. So formulation should be such that whatever is the truncation error associated with the complete equation for each and every term, those truncation errors put together, if we set limit mesh equal to 0, it may involve x direction, y direction, time direction, delta x, delta y, delta t. So all these, delta x, delta y, delta t, if they tend towards 0, then this truncation error has to vanish. Then only the finite difference equation will be, that means different quotient, finite difference quotients, if we put together form the finite difference equation, it will be equivalent to the partial differential equation. We know dependent variable at all x at a time level from given initial conditions. Now let us again consider del u del t equal to alpha del 2 u del x2. Here we have used though u as the symbol, but this u can be envisaged as temperature. So, usually u represents velocity field or velocity. Here, just for generality, we have written in this form, and our tacit understanding or our understanding is that u is temperature. Then del t del time equal to alpha del 2t del x2 is basically unsteady state heat conduction equation. Now this equation can be discretized. That means the specific finite difference forms can be written using explicit finite difference scheme, which is known as FTCS. That means forward in time. In time direction, we have used n as the index. So ui n plus 1 minus ui n delta t forward in time, and central in space ui plus 1 minus ui twice ui plus ui minus 1, all are at nth level, delta x squared. Now from here we can write ui n plus 1 equal to ui n plus alpha delta t divided by delta x square within bracket ui plus 1 minus twice ui plus ui minus 1, all are at nth level. Now this is very convenient to write and very convenient to evaluate also. If at the nth level, value of the dependent variable, that is temperature U, known everywhere, at the next time level, at each location, it can be completely evaluated, making use of the values at the previous time level or at nth level, previous nth level. So this is basically, nothing is unknown here. When we evaluate ui n plus 1, we need at nth level the value of I plus 1, I minus 1. Similarly, for every I, we need the analogous points at nth level. So, and these are known. At nth level, everything is known. So, n plus 1th level, we can find out every value at every location in an explicit manner. Now, the known ui n plus 1 is not only expressed in terms of unknown quantities at n, but also unknown quantities at the time level n plus 1. This can also be written. That means instead of writing this way, the left hand side remains same, but right hand side, these derivatives can be expressed at nth level and also n plus 1th level, even though n plus 1th level, those are not known. So what we can write, ui n plus 1 minus ui n divided by delta t, alpha by 2 has come because at every ith location, we have written basically sum of n plus 1th level and nth level. So ui plus 1, we have written at n plus 1th level and nth level, as if, these two are added, divided by 2, mean value. Then ui at n plus 1th level, minus twice ui, this should be n plus 1. No, this is correct. Sorry, minus twice ui n plus 1, minus twice ui at nth level. So every I location, whether I plus 1 or I minus 1, it is basically summation of n plus 1 and nth level by 2. So similarly, I minus 1 plus at I minus 1 location, ui minus 1 at n plus 1th level and nth level by 2. And then all unknown quantities, that means all the values that are expressed at n plus 1th level are shifted to left hand side. And these are unknown. That means ui minus 1 n plus 1 plus 2 plus 2r by r, where r is a quantity given by alpha delta t by delta x square. So 2 plus 2r by r, ui at n plus 1th level, minus ui plus 1 at n plus 1th level. So these are the quantities, all are at n plus 1th level, and quantities which are at nth level, they are moved to right hand side. And we get this expression. In this expression, we cannot individually find out every nth level like we did in the earlier case, at every ith location n plus 1th level value, but we cannot individually find out them, but we can find out them in terms of their neighbors. And we have to substitute, for example, if we substitute I equal to 2, here we'll get U2, here we will get U1, here we will get U3. All are unknown at n plus 1th level. So I equal to 2, as I said, this will be U1, U2, U3. Here we have written U3 and U2 and U3, but U1 is basically boundary condition. It is falling at the left extreme boundary condition. We have written minus A. Similarly, at I equal to 3, if we substitute, then U will get here U2, U3, U4. So we can see U2, U3, U4 at n plus 1th level, and associated sign and coefficients we can write. So this way, if we keep on moving from I equal to 1, 2, 3, 4, etc. up to I equal to k plus 1 may be the last point. So if we move up to I equal to k, we can see that ui k minus 1, uik plus 1, uk minus 1, uk and uk plus 1, and uk plus 1 is falling on the boundary, so it is substituted by boundary condition. We can see boundary conditions are u equal to d at x equal to l and u equal to a at x equal to 0. So two end points are represented by the boundary conditions, and entire right hand side, these are all known quantities at nth level. So we can rearrange, we can write, a system of algebraic equations which can be now formulated in this way. Basically, if we look at it, we will see principal diagonal that is present, immediate subdiagonal elements are present, immediate superdiagonal elements are present, and this becomes the coefficient matrix into unknown column equal to the known column matrix. A and B we have shifted to right hand side, you can see, and then this equation can be solved very easily, because we'll just read it a little later, that tridiagonal matrix systems can be inverted very easily through an algorithm known as Thomas algorithm. And that is why it is our preference to formulate the problem in such a way that we get a tridiagonal matrix. So here we get a matrix where principal diagonal is present, immediate subdiagonal is present, immediate superdiagonal is present, and this is unknown column, unknown quantities, and this is the known right hand side column matrix. And this, as I said, this can be very easily inverted to know this unknown vector. That means u2, u3, u4 up to uk. We can just inverting the matrix, we can get these values. So this is called, as I said, Crank-Nicolson implicit scheme, and we can understand its difference with explicit scheme. Explicit scheme, we move from point to point, but every point we can evaluate value of that point from the values of the same variable at the previous time level, known values, and other geometrical parameters and physical quantities, physical properties. Here it is thermal diffusivity. But in Crank-Nicolson scheme, we can see that individually values at the next level we cannot find out. Instead, we evaluate them, any individual point, we express them in terms of their neighbor. And this way, we write a system of equations. From that system of equations, we can form coefficient matrix into unknown vector equal to the known vector. In this format, the matrix equation, and specifically here we get tridiagonal matrix, which can be very easily solved by using Thomas algorithm. Now I will just quickly mention about another such solution route, which is fully implicit scheme. That means UI, here instead of U, we are directly using T for the temperature. Ti at n plus 1 minus Ti at n divided by delta T equal to alpha Ti plus 1 minus twice Ti plus Ti minus 1, but all are at n plus 1th level. And n plus 1th level, nothing is known. These values are not known. So we transfer all the unknown values on the left hand side. We can write Ti minus 1 at n plus 1 with its coefficient plus 1 plus again its coefficient into Ti n plus 1 minus again coefficient into Ti plus 1 n plus 1 equal to Ti n. So here if we substitute I equal to 2, this will be T1, T2, T3, I equal to 3, T2, T3, T4. So this way 1 to up to kth point we can go, and we will get again a system of equations. And here on the right hand side, we did not express anything in terms of nth level. So, only this term is expressed at nth level. It comes here. And this will form the finally known matrix when we'll change the indices I as I equal to 2, I equal to 3, I equal to 4. These values will be 2, 3, 4, etc. So this will form the known right hand side matrix, but at the left hand side we'll get the coefficient matrix and the unknown points, variables at unknown points, and we'll again get a tridiagonal matrix. So here instead of calling alpha delta t by delta x square, we have written as f. There is a reason, because although R is a general term, we have written for Crank-Nicholson scheme alpha delta t by delta x square. Here we have given a nomenclature, special nomenclature f, because this term can be called as grid Fourier number. We have already read in heat transfer that Fourier number is given by alpha t by L square. L is the length scale. So when we write alpha delta t by delta x square, then we can call it grid Fourier number. So this forms the coefficient in this discretized equation. This scheme may be applied for all the grid points in the domain from I equal to 1 to I equal to k plus 1. This will generate a system of equations that can form a tridiagonal coefficient matrix, analogous to what we observed for Crank-Nicholson implicit scheme. So this is fully implicit scheme, and also we have discussed today about Crank-Nicholson implicit scheme. Thank you very much for your attention. We will stop here today. Thank you.